So when we were looking at electric forces, we said once we know how to calculate the interaction between any two charges, so what's the electric force between any two particles, any two charged particles, then we could figure out what the net electric force was on one of them in the presence of multiple other charges by simply doing vector addition. Well, now that we know what's the electric field caused by a point charge, we can do the same thing. We can put a series of point charges in space around some point P and now work the vector addition problem that will let us calculate the net electric field at point P due to that series of point charges. So what you'll see is there are some important differences, but fundamentally this problem is going to look very similar to calculating the net electric force because it's still just a vector addition problem. So let's look at an example. So here we have two charged particles that are fixed in the xy plane. Particle 1 carries a charge negative 2 nanocoulombs and lies along the positive x-axis 4 meters away from the origin. Particle 2 carries a charge of plus 5 nanocoulombs and lies 3 meters directly below particle 1. What's the magnitude and direction of the net electric field at point P located at the origin of the given coordinate system? So the first thing we want to recognize, of course, is that I'm being asked to calculate the net electric field at a point in space. Point P here is my point in space where I want to know what the electric field is. Well, there's going to be two contributions to the net electric field at point P. There's going to be a contribution from particle 1. There's going to be a contribution from particle 2. So I know that in calculating each of those contributions, I'm going to need to know how far those particles are away from point P. So the first thing I'm going to do is I'm going to go ahead and again sort of label what my charges are. So Q1 is negatively charged, Q2 is positively charged. Again, that's going to help me figure out what direction each of those charges contribution to the net electric field, which way that will point. Second thing I'm going to do is say, well, I know that that contribution is going to depend on how far away those charges are. So when I look at particle 1, I can see that it is 4 meters away from point P. So if point P sits at the origin, particle 1 is 4 meters to the right of the origin, then the distance between particle 1 and point P has got to be that 4 meters. Particle 2, again, it sits on a right triangle where I know that one of the sides is 4 meters, the other side is 3 meters, and so I can Pythagorize to get that distance along the hypotenuse. Square root of 3 squared plus 4 squared, again, that's 5 meters. Because I know that the electric field contribution is going to lie along the line that connects the particle to the point in space where I'm interested in knowing about the electric field, it's also going to be in my interest to go ahead and figure out this angle theta. And again, with a 3, 4, 5 right triangle, I can use the inverse tangent of opposite side 3 meters, adjacent side 4 meters, and I get that the angle theta is 36.9 degrees. So now I want to go ahead and set up my field vector diagram. So I want to go ahead and draw out what are the two vectors in this case that I'm going to need to add together to figure out the net electric field. Well, there's going to be a contribution from particle 1. Particle 1 is negative, which means the electric field contribution from particle 1 at point P will point towards particle 1. Particle 2 is positively charged. So the contribution to the electric field at point P from particle 2 will point away from particle 2. So again, I've got a field vector that represents the electric field caused by particle 1 that's going to point to the right, and I've got a field vector that represents the electric field caused by particle 2 that's going to point up and to the left. These are the two vectors that I need to add together. I'll do what we normally do. I'll go ahead and draw my coordinate system on top of my vectors. Again, because I know that the electric field contribution from particle 2 has to lie along the line connecting particle 2 and point P. Again, here's my angle theta that I'm going to need to break these vectors up into components. So to get the net electric field, the vector addition problem I'm working is the net electric field at point P is equal to E1 plus E2. So that's the table I'm going to set up to help with that equation. So the net electric field is equal to E1 plus E2. And now I need to break all three of those vectors up into their components. Again, I don't know anything at the moment about the net electric field, so I'm going to leave it in terms of x and y components the way we normally do. E1 points entirely to the right, that's the positive x direction, which means the y component is 0. E2 points to the left, negative x, and up, positive y, magnitude E2, and again it makes an angle theta with the x-axis, so cosine theta goes with the x component, sine theta goes with the y. So there are the components for each of those three vectors, and so it's straightforward to set up my two component equations here. So I'm setting up the equation that the net electric field is equal to E1 plus E2. I'm going to have an x component equation that's going to come from my column on the left. I'm going to have a y component equation that's going to come from my column on the right. My x component equation says that the x component of the net electric field at point P is equal to E1, so all of the contribution from particle 1 plus negative E2 cosine theta. And again, I'm just emphasizing vector addition, and the minus sign is because the component of that E2 vector points in the negative x direction. My y component equation, E1 lies along the x-axis, so its y component is 0, plus E2 sine theta. My two unknowns are the x and y components of the net electric field. I need to go use the expression for what the contribution from a point charge is to the electric field to calculate out the magnitudes of E1 and E2 so I can come back and plug those in. So for E1, K magnitude of Q1 over R1 squared. So again, K times the magnitude of the charge over the distance from the charge to the point squared. So that's going to be 8.99 times 10 to the 9th times 2 times 10 to the minus 9th when I take the absolute value over 4 meters. That gets squared and I get 1.12 newtons per coulomb. So my units for electric field. E2, again the magnitude of the electric field contribution from particle 2, is K magnitude of Q2 over R2 squared. So my 8.99 times 10 to the 9th, that's still K. Q2 is 5 times 10 to the minus 9 with its absolute value. The distance from particle 2 to point P, that's 5 meters, 5 squared, and so I get that that's 1.8 newtons per coulomb. So now that I know E1 and E2, simple enough to come back to my two equations and plug those values in for the magnitudes. So when I do that for the x component equation, I get that the x component of the net electric field is all of E1, so 1.12, minus E2 cosine theta, so that's minus 1.8 cosine 36.9, and my calculator says that's negative 0.315 newtons per coulomb. Y component equation, so the y component of the net electric field is 0 plus E2 is 1.8 sine theta, sine 36.9, and my calculator says that's 1.08 newtons per coulomb. Again, now that I know the x and y components, I can go ahead and sort of sketch out what that net electric field vector looks like. So its x component is negative, which means it's going to point back to the left. Its y component is positive. And again, here's a situation where the y component is a little bit more than 3 times as long as the x. So my net electric field vector points up and to the left and more up than to the left. If I want to know the magnitude and direction of that vector, well, getting the magnitude of the field now that I know its x and y components is a function of just Pythagorizing as always. So square root of negative 0.315 squared plus 1.08 squared, 1.12 newtons per coulomb. And then again, if I want the direction, I can define an angle phi. Again, I've defined it relative to the x-axis, so I want y component over x component inside my inverse tangent. So I've got the inverse tangent of 1.08 over negative 0.315. My calculator says that's negative 73.7 degrees, and so all I'm going to do is translate that to be 73.7 degrees above the negative x-axis.